So in the last lecture, we have discussed about the timing related to combinational circuits. So today we will analyze the timing related to the sequential circuits. So in the sequential circuits, we already know there is a clock or any enable input, and we have understood also the working of JK flip flop, D flip flop, T flip flop, and SR flip flop. So now, in order to understand the timing, we need to understand some of the timing parameters related to the sequential cells. So let us say we are having this flip flop. It is a D flip flop with a positive as triggered clock, and Q is its output. So as far as timing is concerned, there are few parameters. So one parameter is the setup time, right? Another parameter is the hold time. Third one parameter can be your propagation delay. So these are the major three parameters that we need to understand before analyzing the timing related to the sequential cells. So now we will how the setup and hold time are defined. So setup time is amount of time the data at the synchronous input D must be stable before the active edge of the clock. It means the data has to be stable before the setup time before the active edge of the clock. So that is the time defined as a setup time. Similarly, there is a hold time. The hold time is the amount of time the data at the synchronous input must be stable after the active edge of the clock. So setup time is defined before the active edge of the clock, and hold time is defined after the active edge of the clock. Now, how the active clock edge is defined? So active clock can be either rising edge, that is 0 to 1 transition for the positive edge triggered flip flop, and active edge calls and can be falling edge also for the negative edge triggered flip flops. So falling edge means now the clock is transiting from 1 to 0, and for the rising edge the clock is transiting from 0 to 1. So these are defined as the active clock edges. Fine. So next is our propagation delay. So propagation delay is the clock to output delay. That is the D input delay is available at the output after the propagation delay. So propagation delay here defined as TCQ. Similarly, setup time is given by TSU and hold time is given by T hold. Fine here. Now let us say we are given this timing waveform. In this there is a clock CLK, and let us say we are defining the active edge as a positive as triggered flip for the positive as triggered flip flop. So it will be a transition of the clock from 0 to 1, and we are having that edge here. So setup time is saying that it is the amount of time the data input must be stable before the active edge of the clock. So this is my D input, data input. So it means that in this timing the data is changing from 0 to 1 or 1 to 0, but before the active edge of the clock, this time the data has to be stable at least by TSU, at least by T setup, or at least by setup time. So this is here shown here. So it means the data is stable before the active edge of the clock is coming, that is the positive edge of the clock. So it has to be stable at least by TSU time. Similarly, hold time is defined as the amount of time the data at the synchronous input D must be stable after the active edge of the clock. So active edge of the clock is 0 to 1 here in our case. So it means data has to be stable at least by hold time. So this is that hold time. So see here in this window the data is stable. If it is 1 here, then this 1 has to be D has to be 1 at least by TSU time, that is the setup time, and D also should be stable for hold time, that is T hold. So this is the case here. Similarly, propagation delay is the delay from the input D to the output after the clock. So this is our clock. It means TCQ or the propagation delay is the time between the clock edge and the output is getting changed. So this is the TCQ. So this is defined as a propagation delay of the flip-flop after the clock edge comes. Fine. So this is how the three parameters, setup time, hold time, and propagation delays are defined with respect to any timing waveform. So we have to always keep in mind what is setup time. So setup time is the time that data has to be stable before the active edge of the clock. Fine. So this is defined as before the active edge of the clock. So data has to be stable by TSU time. Similarly, data hold time is the time that data has to be stable after the clock edge comes. And propagation delay is the delay from input D to the output after the clock comes. So that is the propagation delay of the flip-flop, TCQ. Fine. So now let us move further. So suppose we are given this waveform. This is a clock waveform. So clock waveform is having it is a positive as triggered here. So this is the setup time window. It means data has to be stable at least by setup time, and data has before the clock edge, and data has to be also stable after the clock edge by the whole time T hold. Similarly, that definition is also valid for the next clock edge, that is a positive as triggered again. So suppose our data input is something like this. This is our D input. So data is changing here from 0 to 1 and clock edge is here. It means this is stable. Data is stable for setup time because setup time is window. Setup time window is this much window. And data is also stable. It is changing from 0 to 1. And after that the clock edge comes. It is also stable for whole time at least. So this D is now 1 at least by whole time. So it is moving forward now. Again the D is changing before the clock edge, before the next clock edge, positive edge clock edge, next positive clock edge, or the next rising edge. So by the whole time, by the setup time. So this is that time again. The data is stable. It is coming from 1 to 0 and it is stable to 0 in the setup time window. Similarly, 0 data is also stable in the whole time window. So this means this is my right waveform for the sequential cell to analyze or sequential cell to receive it properly. Next, let us understand, let's take a case where my data is changing. Now D is changing within the setup time window. So D, it means now it is violating the setup time, right? Because clock edge is here and data has to be stable before the setup time, at least by setup time. But here data is changing within the setup time window. So it means now it is violating the setup time. But it is not violating the whole time because data is stable after the clock edge by whole time at least. So this is now, it means it is violating the setup time. Now come to the next clock edge, next positive clock edge. So this is here again, the data is changing from 1 to 0 within the setup time window. But as per the definition of setup time, the data has to be stable by setup time before the clock edge comes. So here now data is changing within the setup time window, but data is stable after the whole time. Clock after data is stable after the clock edge by whole time. So D is 0. So it means this timing waveform is violating the setup time here also and here also, right? So now let us take another case here. This is my another timing waveform for the data. Here now, see the again the clock edge. This is my positive clock edge. So data is stable. It is 0 in the setup time, but it is violating the whole time because now data has to be stable at least by whole time, but it is not, data is not stable by at least whole time. So it is violating the whole time condition here. Similarly, come here in the next positive edge clock. So data is stable, D is 1 in the setup time, within the setup time, but it is changing from 1 to 0. So data is not stable at least by whole time after the clock edge comes. So it means this timing waveform is violating the hold time here also and here also, right? So this is my correct data input, where it is following the setup time as well as the hold time. Similarly, for the next clock edge, it is following the setup time and hold time. But in these two timing waveforms, either it is violating the setup time here or it is violating the hold time here, right? So in order for the sequential cells, or in order for the flip-flops to function properly, they have to have the setup time and hold time. They should avoid the setup time and hold time violations in every case. Okay. Otherwise, the output of the flip-flops will have a wrong data. So for the correct operation of the flip-flops, it is important to have the setup time and hold time. The data input follow the setup time and hold time. So now setup time is required so that the data can be stored successfully inside the storage device or any flip-flop. So it means if there is any violation in the setup time, then we are not sure that data can be correct data is stored inside the flip-flop or not. So that setup time has to be followed. Setup violations can be fixed either by slowing down the clock or by decreasing the delay of the data path logic. So I will discuss about the this definition, this statement later on with the help of the example. So in the journal, there is a launch flip-flop or a flip-flop that launches the data, and a capture flip-flop, the flip-flop that captures the data, whose setup time must be satisfied. So the setup check validates the long or the maximum path from launch flip-flop to the capture flip-flop. So we are, let us say we are having the two flip-flops. One is a launch flip-flop, the flip-flop that is launching the data, and there is another flip-flop after that that is capturing the data, right? In the two cascading manners. So it means the data has to be stable before the next clock edge for the capture flip-flop. So it must follow the setup time in that case, right? Similarly, the whole time will be followed for the capture flip-flop. So for the whole time violations, the whole time constraints of the flip-flop specifies an interval after the active clock edge. So active edge of the clock. So data must be stable in the interval. So see here again, we are having a flip-flop. The data is given and a clock edge is given here, and we are having this clock waveform. So for the hold time, to avoid the hold time violations, the data must be stable after the clock edge comes. So see here, we are having this kind of waveform for the data. In this, the data is changing from 0 to 1 within the whole time. So this green shadow is showing the whole time window, but here data is changing within this whole time. So it means it is violating the whole time here. But see the another timing waveform for the data. In this, data is stable at least by whole time. So see here, it is 0 and it remains 0 beyond. So whole time is required so that data can be stored successfully inside the storage device. So whole time can be fixed either by increasing the delay of the data path or by decreasing the clock uncertainty, that is skewed. So I will discuss about this with the help of some examples in the further slides. So we must keep in mind that data has to be stable by at least setup time, so before the clock edge, and by at least the whole time after the clock edge. Fine. Otherwise, the proper operation of the flip-flop cannot be assured, or it may have the wrong data stored inside the flip-flop. So the whole time, again, similar to the setup time, the whole time check is between the launch flip-flop, the flip-flop that is launching the data, and the capture flip-flop, the flip-flop that is capturing the data, and whose valid whole time must be satisfied. So because the data has to be stable after the clock edge, so it is valid for the capture flip-flop. Now we will understand how the maximum clock frequency is defined. Suppose we are given some kind of a digital circuit. in the digital circuit we are having some sequential circuit as well as some combinational circuit, and we need to find out the maximum clock frequency. So how do we find the maximum clock frequency for the proper operation of our digital circuits? So we will understand that now with the help of the setup and hold time head time definitions as well as the propagation delay definition. So how do we define the maximum clock frequency? The clock frequency of a synchronous sequential circuit is limited by the timing parameters of its flip-flops. So these timing parameters are your setup time, your hold time, and your propagation delay of the flip-flop, as well as the gate. Gate is a combination circuit. So this limit is called the maximum clock frequency for the circuit. So maximum clock frequency, the reciprocal of the maximum clock frequency will be the minimum clock time period. It means from the maximum clock frequency, I can define the minimum required clock period for my proper operation of the circuit. Fine. So if you have heard that our microprocessor is running at 2.7 gigahertz or 3.2 gigahertz, that is the maximum operating frequency of the microprocessor. So microprocessor is running at that maximum frequency of 3.2 gigahertz. It means the task, some task will be now either will be in one clock period or in multiple clock periods. So that clock period will be 1 by 3.2 gigahertz. So it will come in the form of few nanoseconds or less than nanoseconds. If you divide by 1 by 3. If you divide 1 by 3.2. So the relevant time parameters now for the in order to find the maximum clock frequency, the relevant time parameters will be related to our sequential circuit as well as the combinational circuits. Now for the sequential circuits like flip-flops, so for the combinational circuits like gate, we have the timing parameters. Those are propagation delay of the combinational circuits. It will be minimum TPLH, that is the output when the output is moving from low to high. So that is the minimum TPL is the minimum time the output is taking from output is when the output is changing from low to high, that is TPLH. Similarly, there will be a minimum time period when the data output is moving from high to low. Similarly, there will be a maximum time also for the output to move from low to high, and a maximum time period for the data to move from output data to move from high to low. So min and max definitions are always given in the form in the sequential circuits. Fine. You can also see the data sheets of the various vendors who are providing the flip-flops. They always give the min and max definitions or the min or the max values in the data sheets related to the timing parameters. So similarly to the combination circuit, we are also having the timing parameters for our sequential circuits like flip-flops. So for the flip-flops, it will be one thing is the propagation delay. The propagation delay will also have the min and the max definitions. For the min, again, we will have the TPLH. That is the output is when the output is moving from low to high. The minimum value of the output when it is moving from low to high. Similarly, the minimum value when the output is moving from high to low. So TPLH, TPLH is when the output is moving from low to high. And also the delay or the output is when the output is moving from high to low. So this will be the propagation delay. The delay when the clock edge comes and there is a C to Q, clock to Q delay. So that clock to Q delay will be minimum TPLH, means when the output is moving from low to high, what is the minimum value of that propagation delay? Similarly, the propagation delay min TPHL, that is when the output is moving from high to low, what is the minimum value of that propagation delay? The delay between clock to Q. Similarly, the max definitions will be there, TPLH and TPHL. Okay. And similarly, we will have the setup time and hold time also related to the sequential circuit. So for the combination circuit, we are having the propagation delay because combination delay will have the inputs and the outputs. So output will come after some propagation delay of the gates. For the sequential circuit flip-flops, we will have the more timing parameters. One is the propagation delay from clock to Q, or the output comes how much time the output is coming after the clock comes. Similarly, there is setup time and the hold time. So setup time is the time the data has to be stable before the clock edge comes, and hold time is the time the data has to be stable after the clock edge. So one is before the clock edge and the hold time is after the clock edge. Fine. So let us now have an example. We will understand we will find out the maximum frequency of operation of this circuit. In this circuit, we are having one flip-flop. Now there is another flip-flop, and between those two flip-flop, we are having some kind of combinational network. So this combinational network will have the combinational gates, and or full adder your controller can be inside. So that will be in the form of combinational network, right? Now this flip-flop, D flip-flop is also having setup time and hold time. Similarly, this flip-flop will have also its setup and hold time, right? And there will be a clock to Q delay, TCQ. Mean data will arrive at Q after clock to Q delay. Similarly, for this there will be a propagation delay to TCQ. The after the clock edge comes, how much time the output is, how much after how much time the output is coming at Q, that will be TCQ, right? And a clock, same clock is given to first flip flop, and the same clock is also going to the next flip flop. So this flip flop is receiving the data D from the external side. So this is the main D input. This D input is going through this flip flop and further through this combination circuit, and then is received by this another flip flop. So this will be my launch flip flop, and this will be my capture flip flop. Fine, because launch flip flop is launching the data and capture flip flop is capturing the data. So this will be my now capture flip flop, and this clock is having somewhat time period, that is a T time period, and we need to find out the time T in order to find the maximum operating frequency of this given circuit. Now how do we do that? Let us understand that. So in order to find the maximum frequency of operation or the minimum time period required for the proper operation of this kind of circuit, where we are having one flip flop connected with another flip flop through some combinational network, it will have its own setup time and hold times. It will also have its own setup time and hold times. So it means for the proper operation, the setup and hold time must be valid, or there should not be any violation in the setup time and hold time of this flip flop as well as this flip flop. So we will see now which flip flop will be considered when, in order to find the maximum frequency of operation. So the clock period T should be long enough for the data to propagate through the flip flop and combinational logic and to the setup at the destination of the next flip flop, this flip flop, before the next clock or the next clock edge comes, or before the next sampling of the data. It means if we have sampled some data here in one clock edge, and that data has to be data has to move through this combination circuit and has to come here before the next rising edge comes. Before the next, if the next rising edge come, it will sample the new data. So we have to process the earlier data also. So it means this flip flop should receive this D input through this combinational circuit delay as well as following the setup time of this flip flop, because this data has to be stable at least by the setup time of this flip flop before the next rising edge. After the next rising edge, this will sample the new data and it has to store the previous data. So in order to have the proper operation, or in order to avoid any kind of violation in this circuit, what should be the minimum time period, that we will now find out. So it is very important to understand the problem first, and then how do we analyze this circuit, how do we find the this minimum time period, that we will now understand. Okay, so T must accommodate, it means the T has to be wide enough such that it accommodates, one thing is the clock to Q delay, because data is coming here already. So data will be available at the Q output after clock to Q delay. It means after the clock edge comes, it will take at least by the clock to Q delay of this flip flop, then data will be available here after the clock to Q delay, TCQ. Similarly, data will move through this combination circuit, so it will also have its own delay. So that delay also will be considered in this within this time period. So after the combinational delay, the data will be available here, and this data has to be stable at least by the setup time before the next clock edge comes. So it means this flip flop must follow, or this flip flop must have the setup time, must follow the setup time. So the timing period must accommodate one thing is the clock to Q delay of this, the combinational delay of this circuit, as well as the setup time of this next flip flop. So that is written here. One is A, the clock to Q delay of the first flip flop. Second is the combinational delay, the delay of the combination circuit, and then next is the setup time of the next flip flop, because data has to be stable here before the setup time, at least by the by at least the setup time. So these all three timing parameters must be accommodated within the given time period in order to avoid the in order to have the proper operation of the circuit. So it means my time period T will be the summation of all these three timing parameters. One will be TCQ, one will be the delay of this, and another will be setup time. So T must be more than, at least more than or equal to the propagation delay of the first flip flop plus the combinational circuit delay plus the setup time, right? So this is it. And here also the max definition is coming in the picture, because we are finding out the timing period. So the maximum values must be accommodated within that time period. So that's why we are considering the max values of the TCQ as well as the maximum delay of the combinational circuit. Fine. So this is that time period. So this time period must accommodate the propagation delay of the first flip flop, that is the launch flip flop, then the combinational circuit within the flip flops, and the setup time of the next flip flop. So when this constraint is violated, the destination flip flop will miss the setup time and sample the wrong data. So this situation is called the setup time violation or setup time failure. Fine. So there is one more constraint imposed by the whole time. One earlier constraint was by the setup time. Another constraint will be by the whole time of the flip flop. So this constraint ensures that data input is held constant after the clock edge, that is the whole time. So the whole time must be lesser than the minimum clock to Q delay as well as the combinational circuit delay. So for the whole time, the min definition comes in the picture. Okay, because at whole time is the time that data must be stable after the clock edge. So data has to be stable at least minimum by this much time, the whole time. If data is stable by the max values, then there is no violation, but data has to be stable at least by the minimum values also. So that's why the min values of TCQ and T combinational are coming in the picture for the whole time definitions. For the time period, the max values come in the picture. Okay. So the whole time of the destination flip flop must be shorter than the sum of the minimum clock to Q delay of the source flip flop as well as the minimum propagation delay of the combinational logic between the circuit. Otherwise, there will be a whole time violation. So let us understand this with the help of an example. Suppose we are having this circuit. In this is one flip flop. There is a combination circuit, that is a mux, 2:1 mux. It is a combination circuit between the two flip flops, and there is another flip flop here, and same clock is going to both the flip flops. And suppose we are asked to find out the maximum frequency of operation of this circuit. So we will follow the same definition of the time period, how we have defined the time period in the previous slide. So this is our clock here, CK. and we have to find out the time period TW. So this time period will tell us that how much time is required for the proper operation of this circuit. So what is the minimum value of TW? So TW has to be at least more than this, such that it can accommodate the clock to Q delay of this flip-flop plus the delay of this combination circuit plus the setup time of this. Fine. So it means the once the data is available here, the Q naught will be available after TCQ delay of the first flip-flop. So that is this. So see here, Q naught is available after TCQ or TPFF here. Similarly, there will be a combination circuit delay of the mux. So it means that there will be a propagation delay of the mux, TP mux, and data has to be stable by at least the setup time before the next clock edge. So it means that time period TW must accommodate the propagation delay of this flip-flop plus the combinational delay of this mux plus the setup time of this. So it means this is the time period or the maximum frequency required for the proper operation of the given circuit here. Fine. So let us understand with the help of another example. Suppose we are given this flip-flop here, D flip-flop. It is a positive triggered flip-flop. The output of the flip-flop Q is fed back to the D input through an inverter. And we are given the propagation delay of the inverter is 2 nanosecond. The flip-flop has a propagation delay of the 5 nanosecond. And setup time of the flip-flop is 3 nanosecond. It means the Q is coming here. Q will move to D after 2 nanosecond of the flip of the of this delay of this inverter, and it has to be stable before the clock edge by 3 nanosecond, because the setup time of this flip flop is 3 nanosecond, and propagation delay of the flip flop, that is the delay from clock to Q, that is 5 nanosecond. So let us say we have this timing waveform where clock is coming and Q is coming after 5 nanosecond and inverter delay is 2 nanosecond, and we are having this timing, the clock edge is coming, but the setup time required for the required for the flip flop is 3 nanosecond, and data is coming here. So it is now violating the setup time window because it is moving from 0 to 1 within the setup time window. So it means now that it will violate the setup time. So we will find out the maximum frequency or the maximum or the minimum time period for the proper operation of this kind of circuit. See another timing waveform where we have extended the clock. So now clock is this. So from the positive edge of the clock, there will be a 5 nanosecond delay, that is clock to Q delay. So this time period must accommodate one thing is the delay of the flip flop. Then is another delay, that is the delay of the inverter. So that is 2 nanosecond. And the next rising edge is here, and data has to be stable within that time period, but data is coming here and after that it is stable. So it means there is no setup time violation. It will work properly because data is stable here and it is stable within the setup time of the flip flop. But here, because the timing period has been extended larger than the required, it is more than here by 5 nanosecond. So it means my circuit will although work properly, but it is not the maximum frequency of operation or the minimum time period. So what I can do now, I can reduce my time period by at least 5 nanosecond, because now data is stable here and it has to be stable by 3 nanoseconds the setup time of the flip flop before the next rising edge. So it means I can increase the frequency of operation by reducing this much time period, 5 nanosecond. So that is this here. See here, this is the propagation delay of the flip flop, that is C2Q 5 nanosecond, and another time is required for the data, output data is coming through the inverter to be stable at the D input, that is after 2 nanosecond. So that is after 2 nanosecond, and 3 nanosecond is required for the setup time of this flip flop. So this is this here. So it means now the maximum or the minimum time period required for the propagation of this circuit is 5 nanosecond plus 2 nanosecond, that is 7 nanosecond plus a 3 nanosecond, that is 10 nanosecond. So for the proper operation of this flip flop, at least the time must be 10 nano, timing period must be 10 nanosecond. Here 5 nanosecond is extra, so it is having 15 nanosecond. But my required time period is 10 nanosecond for the proper operation of this flip flop. Okay. So this is how setup time and hold time and the propagation delay of a flip flop is helpful in finding out the maximum frequency of operation. So this circuit is different from the earlier circuit. In the earlier circuit, we were having two flip flops. One was a sampled flip flop, one was capturing the data, one was sampling the data, another was capturing the data, and there is a combinational circuit in between the two flip flops. But here we are having a single flip flop. Single flip flop is receiving the data from the output through our inverter, and there is a propagation delay, clock to Q delay of the flip flop. So for the proper operation of this circuit, the time period must accommodate one thing is the clock to Q delay of this flip flop. Then output is coming to the input, and there is a inverter. This inverter is having the propagation delay of 2 nanosecond. It means the clock is Q is coming here, and it will reach D after 2 nanosecond. But there is also setup time required for the flip flop. So it means data has to be stable by setup time, and setup time is 3 nanosecond, right? So it means the time period must accommodate one is a clock to Q delay plus the delay of this combination circuit, that is the inverter, plus the setup time of the flip flop. Fine. So this is how do we calculate the maximum frequency of operation of a given circuit. So this combination circuit can be a different circuit here. It is an inverter. It can be NAND gate, NOR gate. So in that case, the delay of that gate will come in the picture. Or if we are having a multi-path circuit here, like min and max path, so we will find out, because we have a maximum propagation delay comes in the picture while calculating the maximum frequency of operation. So we will find out the delay, maximum delay of the combination circuit. Okay. So please keep in mind this thing, because these concepts are generally asked in the interviews. So generally what they do, they replace this combination circuit with the multipath combination circuit, in which we are having the min path as well as the max path. But from the definition of the this time period, we have a combinational delay, that is a max combinational delay. So we need to find out the max delay in the combinational path in that case. Okay. So please keep in mind this thing. And for the whole time, the min definitions come in the picture. That is for the capture flip flop, for the next flip flop. So now clock skew, we will define the clock skew. How the clock skew is defined, we have discussed it earlier in my previous class, the latency of the clock and the clock skew. So let us again go through it.